Started. Today we are actually moving into some territory that you probably have not seen before. We are going to talk about random numbers, which you may have seen before, and exceptions, which I doubt you have. We'll spend most of the time on exceptions today, but we will start with random numbers. So it is frequently the case when we are solving a problem that we need random numbers. Think of the Powerball lottery. Okay, these days the winning numbers are generated using a computer. And what you need is some random numbers, because if they're not random, someone could predict what those numbers would be and easily win the jackpot. When you're doing simulations, say for how a volcanic eruption is occurring, you need to be able to generate random numbers for the activity. Just if you're pretending to flip a coin or throw dice, you need to be able to generate random numbers. And mathematicians have spent a lot of time coming up with algorithms that generate numbers that look random. So we talk about pseudo-random number generators because they're not truly random. The only way you get truly random is maybe flipping a coin or doing something else. But they have devised algorithms that basically, when you feed the numbers into something that, quote, can detect random numbers, it says, yes, this looks like a stream of random numbers. So the C++ provides a random number generator. It's the RAND generator, and Dr. Planck doesn't think much about it, but it is fairly commonly used. It generates, the RAND generates a random number, I believe, between 0 and a couple billion. Then there are other random number generators also built in C++. DRAND will produce a random number that is a double. LRAND will produce a random number that's a long. I think the developers of C++ have put more effort into refining their random number generator. So in general, you would probably want to use that. Dr. Planck's research group uses something appropriately called the mother of all RNG, or random number generators. And that is the one we will probably be using in this course. In the past, he used the RAND one. I haven't checked the future labs, but given this little discourse here, I would assume he plans to use it as well with other programs. I think lab 4 or 5, when we get to it, will probably be involving that. At any rate, it does have a header file that you will include in your programs when you are using it. And it is defined as a class. It has different functions for generating different types of random numbers. So random double produces a random number between 0 and 1. And you'll notice over here, it actually will not produce 1. If you notice the mathematical notation, that's a parentheses. The second one is a right square bracket. So the second one stands for double inclusive, because you could get 1 as a random number. And then random integer generates a random number between 0 and 2 to the 31st. It's an int because it could be, well, supposedly could be negative, but it can't because it's between 0. Unsigned ints for 32 and 64. You can even get bigger than that. We won't worry probably about the rest of them. So the ones you're probably most going to be concerned with are these 5. And in fact, I would venture that it will mostly be these 4. Then another important thing is you typically need to seed your random number generator. That's the first number it uses. So the random number functions take a number, and based on the previous number that was generated, they generate the next number. So they need a number to start, and that is provided via the seed function. Often you use the time function to seed the random number generator because that produces a different number each time. So I'm actually, let's see, he's got his MOA, but I'm just going to, for a moment, use the C random number generator. So let's just generate some random numbers. And you can see standard lib that has the 1. So we are going to generate, we'll say 10 random numbers and print them out. And I will generate 5 random numbers and print them out. Okay, very simple. Let's create another window here. Use another window to do the compilation. And it doesn't like that. Why not? Did we not write this file? Nope, we did not. Okay. So it generates, as you can see, some random numbers. Let's run it again. Same thing. Run it again. Same thing. It doesn't look like we're getting anything different. That's because we're not seeding it. Okay, so now we will seed it with 0. So the function is seed. We'll recompile it. It doesn't like seed, so let's look that up, see what the seeding is. It's srand. So seed the random number generator, so it's srand for seed the random number generator. And we run it, we get different set of random numbers. But if we run it a second time, we get the same set, which is good if we're just debugging. But in general, we don't want to produce the same set. So we often seed it with the time function. Times 0 gives us the current time. So just to show you, times 0, we'll print it out. I also need to include the ctime library, so that's where this is located. I run it, and I should have output. Redo it. So you can see time equals some large number, then some random numbers. We'll do it again. And it looks superficially like 172, 172, but now if you look a little more closely, it's 69 versus 68. So the random numbers really are different. The time is the number of seconds since January 1st, 70 or 72? 70? Pardon? 70. Okay. So the number of seconds since January 1st, 1970. And a few years ago, actually many years ago now, it went over 30, it went from 31 to 32 bits. And I know that because I had a program that inexplicably broke. that used time. And it was because at 31 bits, that's a positive integer. At 32 bits, do you know what happens if you're not careful? It can make it a negative number because it can interpret that 32nd bit, if it's a 1, as a negative number. And all of a sudden, my program broke because it was generating negative times, and it was just fluky. Turned out I had to change the integer to an unsigned int. That way. Pardon? There we go. I just made a time machine and went back in time. Okay, so questions about that. Okay, now the big thing with random number generators is what you do with the return value, because it's generally a pretty big integer, as you see there. Let's say we want to generate a program that throws dice. So we want a number between what? If we're throwing 2 dice. 1 and
6.
2.
Oh,
1 and 12.
Or 2
Okay.
and 12.
If it's 2 dice, very good. We want 2 and 12. Okay, so the trick is to convert the numbers to between 2 and 12. So the book had an example of that. I will go over it and then have you write a quick program to do it. So let's say we want to generate a random number. Showing up, yep. So we want to generate a random number in the range x to y inclusive. Okay? So we get our random number. So we'll say that we have our random number is in R. So R is our random number. Okay, and we can be pretty confident it's not yet in the range we want. So the first thing we want to do is to make that random number fall in the range x to y. And we can do that by modding this random number, so the mod operator, with x minus y plus 1, because that gives us the range of numbers we want. Let's say we want it something in the range 2 to 12. Okay, that gives us 12 minus 2 plus 1 equals 11, which, if you think about it, is the right on a die, throwing 2 of them, you can get 11 different outcomes. Okay, so our mod, and that will give the remainder. Remember, mod gives us the remainder. So in this case, with x being 2 and y being 12, we would get r mod 11. That would give us a number between 0 and 11. Now, that doesn't give us a number in the range 2 to 12, so we have to next add the beginning of the range to that, which is x. So in this case, it would be x plus r mod 11. So for example, if this yielded 6 and our x is 2, we would end up with 8. Okay, and checking our extremes, if this mod produces 0, 2 plus 0 would equal 2. That's good. And if it produces, what's the maximum number r mod 11 can produce? 10. It cannot produce 11. So that gives us 12, and that's indeed what we want. So we kind of verify here that we have hit our ranges. Okay. With random numbers, by the way, you typically use unsigned ints because you don't want a negative random number generally. You can always convert it. 1 second. Okay. So you normally don't want negative random numbers, or let's put it another way. The random number generators don't return negative numbers. So, but they may return 32-bit ints. And remember that 32nd bit is a signed bit. So you typically want to declare your variables that hold your random numbers as unsigned ints. Okay? Yes. Yes, very good. The question is, did I mean y minus x here? And I absolutely did. Thank you so much. I meant to say y minus x plus 1, because y is the greater value. So that is what I meant to say. Okay? We all good with that? Well, good. Why don't you go to Canvas in that case? And we have a challenge problem for you to work on. If you don't have your cell phone with you and can't get a push, you may need a push. You can do it on your oops. There is an assignment for today. On the after class. And what I want you to do is the second challenge problem. And I'm going to put it up if you don't have it, because you can easily do it on a piece of paper or on your computer if you don't do it. So the challenge activity is to generate two random numbers. Whoops. We want to generate two random numbers between and including 100 and 149. Okay, so you're writing two statements that use rand to print two random integers between 100 and 149, inclusive. And you end with a new line character. So if you don't have the ability to get it, they read in a seed value, they seed it, and now your solution goes here. So it's going to be two cout statements involving rand. You can certainly do this on paper if you can't do it on your computer. And it's fine to work with someone else on it. While y'all are doing that, I need to go get a drink of water because I forgot a cup.
Dude, I don't know if it was the funniest thing that it ever happened to me, but I'd be in so many league games out of nowhere. My computer. You can say what you did.
You had to go and like modify like some file like deep down in like System 32.
So, or if you haven't finished it, I am going to go over the solution. So, we're going to be printing out a random number, so we'll use rand in this case, and we are going to be modding it. So y in this case is 149, x is 100, and then we add 1 to it to get 50. And we also have to add x, which is 100, and that should give us our result. And because, well, we'll just copy and paste because it should be the same statement twice. So we run it, and we pass our tests. So take the random number, mod it with 149 minus 100 plus 1, which gives us 50, and then add to that x. Okay, pretty simple, but while we'll put it aside now for about a week, we will be coming back to it by next Tuesday, I believe. And if it's not next Tuesday, then it will be shortly after that when we get to hashing or hash tables. Yep. So starting, in fact, next week on Thursday, we'll get to hashing, and then we'll be using random numbers big time. Okay. So questions about random numbers. In that case, we'll move on to exceptions. And let's see. Let's do it this way. So an exception can be one of a number of things. It could be an unusual event, which is either erroneous or not. It could be, it should be detectable by the hardware or the software. And it may require special processing. So, examples. When you reach end of file. So that's an unusual event, but it's not erroneous. Okay, so I just put not erroneous, but unusual. Okay, bad input. That is erroneous and unusual. Okay, division by 0. Okay, erroneous and hopefully unusual. Okay, subscript out of range. Also erroneous and unusual. Okay, so in all of these cases, you generally want to do some special processing. And the thing that does the special processing is called an exception handler. It is a code fragment that processes an exception. Now, up to now, you've seen two ways of doing exception handling. Okay, so I'll say ways to handle errors. One is to have a function return an error code. Okay, so for example, cin returns false on failure. Okay, that's probably the most common way that you have dealt with errors to date. Okay? Another way is with a so-called signal from the operating system. And you actually have sometimes seen that when you get a seg-v for segmentation or a sig-bus error. Okay, you've probably seen one or both types of errors when your program crashes. That is, SIG stands for signal. SEGV stands for a segmentation violation. That's when you try to access a piece of memory that is privileged and you're not allowed to access, such as the operating system. SIG-bus is when you try to access a piece of memory that's not properly aligned on a boundary, such as trying to access a double that's on an address that's not divisible by 8. That would get you a SIG-bus error. Okay? And as you've seen, these signals tend to be lethal to your program. Your program exits immediately. Turns out you can write signal handlers for them, but it is frowned upon. Typically, only people who write operating systems write such signal handlers, and that's for the operating system itself. So today we're going to introduce a third type of way to handle it, which is with something called the exception class. Okay, or exceptions, and it uses try, throw, catch. So that's what we're going to be talking about today. And these may be either generated by the system or the runtime environment or by the programmer. So either one. So the general format of try, catch, throw is that you have a try statement that goes around the code that you're worried may have some type of error in it. And you see it's got a block, so it looks just like a block for a for loop or an if statement. Then you have an optional catch statement that catches the exception. And when you want to generate an exception, you use the throw statement, and you throw some kind of value. That value can be a primitive type like an integer or a float. That's pretty uncommon. It could be a string. It could be an object of a class. People differ in their preferences of what they throw. Dr. Planck likes to throw C++ strings and is a strong advocate of them. The book has you throwing exceptions that are instances of the C++ standard library runtime exception. I'm not a strong advocate of any type. I think whatever works, works. In this course, since Dr. Planck is a big advocate of throwing C++ strings, that's what we'll do. But I also will show you the exception classes provided by the C++ standard template library. You'll notice that you have to cast the strings you throw to C++ style strings because otherwise they are, the type is a const char star, which I'll show you in a moment. So here you can see what I'm doing is I am trying to convert command line arguments to integers, and if it fails, I'm throwing a string that says what is not an integer. Okay? And then down here I catch it, and the catch statement, the type of, takes one parameter. The parameter should match the type of the thrown object. So here we threw a string. Down here we catch it as a string. We print to the C error, and in this case we return. Okay. Now, let's say we didn't return. Let's say that instead of returning, we continued. Where would execution continue is a legitimate question, because often we want to recover from our exceptions. The answer is that we continue with the statement immediately after the catch. So in this case, if we did not return, we would proceed to the printf statements, which obviously in this case would be a mistake because some of those variables are undefined. But we do not pick up execution after the throw. So let's say that we immediately failed on A and threw a string. After we do the exception handling, we would not continue here. Instead, we would continue here after the try. This code right here is called an exception handler. It is our code fragment that is handling the exception. Okay? And you can see that this is not the error message being thrown to the user is not particularly helpful. Okay, and you will sometimes hear me harp on this during this semester, the necessity of generating useful error messages. So if you are a user using this program and you see A is not an integer, why is this not particularly helpful to you?
Usage message.
So you haven't seen, well, what do you mean you haven't seen the usage?
Like, A is a name you use in the usage message.
Right.
It's really the first argument you give.
Very good.
They don't know that.
Right, very good. So essentially, you're assuming they know what the program looks like, which they don't. They haven't seen the source code. So this might be useful to you when you're debugging because you know that A, B, and C are variables in your program, and you also know where you're handling them. The user presumably has never seen your program or the source code. They have no idea what A is. It would be much better to say that your first command line argument is not an integer. Or if B is the problem, it'd be much better to say that the second command line argument is not an integer. Quite frankly, it would also be nice if you would print out what that argument was, okay, which you can't do here because you are throwing a string. One thing that you could do at this point is you could use a OStream object, which I know I haven't really covered a great deal, and that's because they just don't come up a lot. But you could use an OString object to format the string so that it would say command line argument 1 is not an integer and actually print out command line argument 1. Another thing you could do is you could create an object. And I know we're not getting to classes until Tuesday, but you've seen classes before. So what you could do is you might define a class, and you might call it command line arg exception, and you might have protected the command line value. So, and you might have int position to indicate, or index to indicate which of them is wrong. And then you'd probably have a constructor, in this case taking two values, the value v, or the error value, and the int, the position, and we could set the value equal to error value, And we could set the index equal position. And we might also then have some public methods. Int get index, which returns the index. And string which returns the value. Okay, and probably it would return a reference, but we won't worry about that too much now. Okay, so this would allow us to actually throw an object. So now when we did the throw, we would throw command line arg exception, and we'd throw arg v1, and the position would be 1. Or we would throw command line argument exception 2 and 2. Okay, and that would allow us to add information to our exception. Okay, this is one reason why I'm not actually as big a fan of throwing string objects, because it limits the amount of information that you can pass to a exception handler. And if I wanted to catch it, so I might have try in this case, blah, 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 my throw, and my catch statement now would look like catch command line argument exception. And typically, you catch it as a reference parameter, and then you do something with it. Okay? So this is called a user or programmer defined exception object. So this one right here is a programmer defined exception class. So you're allowed to define your own exceptions and throw them. Okay, two different approaches. One, Dr. Plank's throwing a string. Another, where you throw your own defined exception class.
Bless you.
Thank you. Okay, so questions about the basics of try and catch. Okay. The idea behind using the try-catch construct is that you separate your error handling code from your normal processing code. Otherwise, what can happen is you start to intermingle your error handling code with your normal program logic, and it can be confusing. So the idea is to try to gain a clean separation between the two. Okay? That's the idea behind these try-catch constructs. Okay, so the basic idea is pretty simple. And you can have exceptions that are thrown for you. So that's what happens with the at method in a vector. So if we go and look at a vector, and we, in this case, I'm going to say for I equals 0, I less than equal to nums.size. I'm going to use the at to try to assign, and there's a bug here, which we'll see in a moment. Actually, I don't want a 2D vector, I just want a 1D vector. Okay, so if I run it, well, where's my extraneous closing bracket? Probably down here. And I get terminating with an uncaught exception of type standard : out of range, vector, abort trap 6. What has happened is that this STD : out of range is an exception class predefined for you by the standard template library. And when you get a out of range subscript like you do here, it throws an error. Notice I never caught it. Now I'm going to go back and I am going to catch it. So I'm going to try, and I am going to catch a STD out of range exception, and I'm going to print it using what's called the what method to standard error. So the what method, we'll go over it in a minute, but it prints whatever the error message is. Okay, so in this case I caught it. So I'll compile, and it printed out vector. But it then no longer says terminating with an uncaught exception because I actually caught it. Okay, and notice over here, that was the what message too. It's very uninformative. You really wish it would tell you what the subscript was and maybe some line information where it occurred, but it doesn't. So it's not nearly as helpful as you would like. I am going to show you that execution comes up after the, so still in try. Okay, and here it is after try. So I'm going to show you that the execution does pick up after the try statement, not in the try statement. So see, we are after the try. So after we handle it, we come out and we're there. Yes? Yes, so the question was, is there a question why I made this parameter pass by reference? And it's, again, because I want to avoid copying the object because it's expensive, okay? Normally, I would actually go a step further and put down here const to indicate I'm not modifying it. But the big reason it's a reference parameter is I want to avoid copying the object because it's expensive. Okay, so as I said last time, you really want to try to get in the habit of passing objects by reference. Okay, other questions? Okay, so as you can see, you're not getting a lot of information here. I want to show you that GDB could give you a lot more information here. So I'm going to copy this program over to the Hydra machines. And I'm going to log into it. And I'm going to compile this thing using the -G flag, so it compiles it with debugging information. What doesn't it like? Unexpected ID. So it looks like I need it to include the exception library. I think it's unhappy that I did not use the exception library. Still not happy. See if that works. that doesn't work. That worked. Okay. So the standard exception library on our machines is stdexe. So on my Mac, it was happy not to have it included, but on the Hydra machines, you have to include stdexe as the exception handling library. Now I compile it. And it still didn't like it. Okay, sorry. Let me find out what I need to compile it with. And not there. std accept. See how it likes that. There, it liked it. Okay. So it's std accept. Used to be exception. I guess they like now to put std in front of it. Okay, so at any rate, I compiled it with the G option. I now run it. Okay, after the try inferior, actually I didn't want it to exit normally, so let's get out of there. So I'm no longer going to use the try statement. So I'm just running it with numstat at to show you that GDB will give you a lot more informative information. Okay, so now it's starting the program. Terminate called after throwing an instance of std out of range. What vector range check at? Okay, this doesn't look so useful, but I can do a BT for backtrace. And it's telling me that if I go all the way back to the top, I was at v.cpp10. Okay, so now if I do a list, actually if I go to up to 9, so up says go up to stack frame 9, and now I do a list. I see that I was at nums.at. That's a lot more helpful, right? I see that my termination threw right there. Now I can print I. I is 5. That might give me some idea of what's going wrong. Might or might not. At this point, you have to know that you started with zero-based indexing. The point is GDB will terminate right at that point, and you would see right away where your error was. Okay, so in this case, the try statement isn't quite as helpful, but just because the exception message is pretty uninformative, which is too bad. It'd be a lot nicer if it would give you line information, but it doesn't. Okay, now some bugaboos with try statements. Going back to Dr. Planck's notes, somewhere he's got const. No, he doesn't. Okay, well, I'm going to take his code. I thought he had const. Okay, here we go. So here he does the same program. He throws it, but now he doesn't cast this to a string, right? And he runs it, and what he gets is terminating with uncaught exception of type char star const star. So the problem is if you just throw a string, the type is char const star. So you need to be careful if you're going to throw strings that you cast them to a C++ type string. So that's one gotcha. Here's another gotcha. I am going to, let's see. Try, still in the try catch. I am going to print out not just the CR statement, but I'm going to print out I equals. Okay? So I'm printing out now not just the error statement, but I'm also printing out what the subscript was. Okay, I compile it, I run it, all is well, it printed out I equals 5. Just a second. Okay. Now, I'm going to move the I into the try statement. So now the I is declared inside the try statement. And now I get an error message, use of undeclared identifier I. And you're like, wait, what? I declared, here's I. Why is I undeclared? The scope. Once I threw the exception, I came outside the try statement, which meant I left the scope of the try statement and the I became undeclared. That's a common gotcha with try statements. You think that the exception handler should have access to the variables that are declared inside the try statement, and you don't. Okay, if you use Dr. Planck's preferred style of declaring all your variables at the top of the function, you'll never run into this problem, but hey, I'm a realist, and I know that doesn't always happen, so that's a gotcha with try statements. If you want the variable to still be in scope, you need to declare it outside the try statement for your exception handling. Okay, couple more things about catches that aren't so relevant right now, but good for you to see it. And then we will hit it again later. Before I do that, question? You had a question? Or did I answer it?
Yeah, I pretty much answered it.
Okay. So you may not know what type of exception you're catching. So if that's the case, you're allowed to use a catch ... that catches any type of exception whatsoever. Now the problem is you don't know what the type of the exception is, so you can't print any type of coherent error message. So it's not all that commonly used, but you will see it, so you should know what it is. You're also allowed to have multiple catch statements. So I could have catch string S here, or E, and then I could have another catch statement, std out of range. So you're allowed to have multiple catch statements, and they are matched in the order that they appear. So you would first try to match the thrown exception with a string. If that doesn't match, it would come down here and try to match this one. If it doesn't match anything, we say that it is thrown out of the function and up the call stack. Okay? So that's what Dr. Planck shows next, is that you don't necessarily have to catch the exception where it is thrown, but you could catch it in another function. So here he has a function A, and all he does is a throw, and you'll notice the throw is not encased in a try. That's fine. It simply means that you're not planning to handle the exception in this procedure. And we say that the exception is thrown out of the procedure and up the call stack. The procedure is exited normally, and all of its variables are deallocated. Any destructors are called, and the error is thrown to the next calling function. You see here, I did have a try statement around the call to A, and I catch an int, and I print out I caught an integer I. So what happens here is main catches the exception and prints it. And if you run the program, you can see it says calling A with this print statement right here. Then A says it's called and is going to throw an exception of int, which it does. Now it throws 5, and you'll notice we never get to this statement right here. This statement never prints out. Instead, we get down to the catch statement. It prints, I caught an integer. Caught an integer 5. Notice this statement right here never executed either. Okay, you should be able to trace through the code, and if I were to ask this kind of question on a test, hint, hint, you should be able to get the right kind of answer. This is a beautiful test question. Lots of potential printf statements that might or might not get executed, and you're having to make your way through it and show me that you understand how exception handling is done. If you are smart, you will make sure that you are able to read this type of code for the first midterm. Okay, because Brad is good with his promises. Okay. Now, Dr. Plank has his advice with exceptions. Everyone has their own feelings about exceptions. Okay, Dr. Plank doesn't like throwing an exception in one method and catching it in another. Well, STD library is constantly throwing exceptions out of their methods. They don't typically handle their exceptions. Like the at method for a vector, it throws it, it doesn't handle it. Okay, so a lot of times you really don't know how the program wants to handle the exception. Maybe the program wants to terminate, maybe it doesn't. So I could make an equally strong argument that, in fact, unless you really know how you want to handle the exception, you should throw it out of the procedure and not handle it. Let the user or the program figure out what it wants to do. Okay, so I understand he's very allergic to throwing it out of a procedure, but I see good reasons for doing it. Okay, again, he is old school and he likes to have procedures return error values instead of exceptions, but again, that's really going to depend on where you are. A lot of more modern theory is you should throw the exceptions rather than have procedures return error values. The reason for that is, let's say you have the procedure return an error value. Well, then how do you return a value from the procedure? Because procedures can't return multiple values, at least not in C++. If you're fortunate enough to be using a scripting languages allow you to return multiple values from functions. That's great. But the problem is, if you want your procedure, let's say the procedure is to sum up a bunch of integers from a vector, wouldn't you like your procedure to return that sum? Now if you have to return an error value, well, you could do that through a reference parameter, or you could return the value through a reference parameter, but there's problems with having your procedures return error values. Okay, and the idea is that when you throw an exception, the procedure returns, you assume the procedure returns normally, returns whatever value it is. If it doesn't return normally, you catch the exception and you handle the exception with an exception handler in a separate part of your code. Okay, so he does say generally try to catch it in the calling procedure. That tends to be a pretty good piece of advice. But sometimes if you want the exception to terminate the program, you might catch it all the way up in the calling program. He says try to throw strings. I'm fine with that, but I'm also fine with throwing exception objects. That gives you more information. Again, he doesn't like throwing multiple types in a single try clause. I don't have a problem with that. You simply have multiple catch statements. I agree absolutely with keeping your try clauses small. You only want to have it around where the error could occur. Okay, the reason you like to use exceptions rather than exit. So I don't like to see exit down in a function. Okay, if you're going to want to exit the program, throw the exception out to main and catch it in main. The reason is that when you throw an exception, it pops the stack frames in an orderly way. When you pop stack frames, they deallocate any objects you created. Some of those objects may have allocated resources from the operating system. If you do not deallocate those objects, those resources may not get returned to the operating system. That's bad. Okay? So the reason you don't exit from a function with the exit command is it may leave, so it's important enough that I'm going to write it out for you. Okay? Don't use exit to return from a nested function. Okay, and the reason is if you do so, you may fail to return resources to the OS, and these resources will remain unavailable. Okay? So maybe you are using another program, another processor to do something, and you fail to tell that other processor that you're done. So that processor sits there spinning its wheels thinking you're still executing. That's a CPU that's offline. Okay? Instead, throw an exception and catch it in main. Okay? This way, all stacked frames are unwound and any resources allocated in those stacked frames are returned to the OS by their destructors. This is really important. Okay? It is really bad form to put an exit call in a nested function. Okay? That's what exceptions get for you, is a orderly unwinding of the stack frames, an orderly return of resources to the operating system. Okay? It also allows you to say what you want to do. Let's say you have open files. Well, should those files be closed and should they exist? Or should the files be thrown away? You get to make that decision rather than the operating or the C++ runtime environment making an arbitrary decision for you. Okay? So I cannot strongly emphasize enough, don't use exit in your programs. It's just evil. Okay? So, last thing before we take off today. There are a set of standard exceptions that are provided by the operating system. So, the standard exception provided by C++ is std : exception. Okay? It has a method called what that when you call it returns a string indicating the nature of the error message. So it's always fine to make your classes be subclasses of std exception. There are a number of predefined exceptions in C++. One is bad alloc. We haven't gotten to that yet. It's when you allocate memory. Bad cast. In 102, you may have learned about dynamic casting. If you do a bad dynamic cast, it will throw a bad cast one. There are certain runtime errors, such as if you get an underflow error when arithmetic underflow occurs. Division by 0 causes an overflow error. So these, again, are exceptions classes. There are certain kind of system errors that everyone always thinks they can use to catch segmentation violation faults. You can't. So signals that are thrown from the operating system like sigseg and sigbus are not actually catchable by C++ exceptions. That's a completely different exception handling mechanism. Then there are logic errors like out of range that are thrown by a vector and some other classes. Length errors that could be thrown. For example, if you try to resize a vector or a string and it's not big enough because there's not enough memory to accommodate it, you can get them. So these are errors that you could catch. Again, if you want, you can make your error messages be subclasses of it. Also, in the book, they have yet another type of runtime message. So it was runtime. They have it as runtime error. So that's yet another type of exception that you can create. So I'm easy as to how you throw your exceptions. If you want to throw them as C++ strings, that's fine. If you want to throw them as runtime errors, that's fine. If you want to throw them as your own classes, that's fine. Okay? Remember the standard except library to include that if you're going to use C++ defined exceptions. And the final thing, remember that the basic syntax is try. If you want to catch something, you can put a set of catch clauses after that. And the way you throw an exception is with the throw statement, which actually is not shown here because that throw is being generated automatically. But throw if you want to throw something. Okay, so that's it for today. Next Tuesday, we will be getting into class.